All right, class, we're going to get started. Okay, so before we get started today, any questions? Kick off. All right, so today we're on lecture 16. This is about two-factor ANOVA. So we're going to talk about how we can essentially use analysis of variance or ANOVA in cases where we have more than one factor that we're trying to investigate. And so we're getting into really a lot more of the power of ANOVA beyond what we showed in the initial introduction. Just a note on the quizzes. I'm still in the middle of grading your quizzes. Hoping to have that done by Wednesday so we can talk about it on Wednesday at the end of class. And yeah, any questions on anything? Last chance. Okay, so today we'll talk about two-factor ANOVA. On Wednesday, actually, we'll talk about p-factor ANOVA, so when we have some number of factors greater than two, but we're going to start with just having two factors. So just as a review, when we discussed ANOVA for a single factor, for example, we looked at Major League Baseball. This was in lecture 11. So we had one factor there with four levels, right, which is basically the position that the players played. And we then use that to investigate the impact on-base percentage based on what we saw in those as a function of the player positions. So this is called one-factor ANOVA or analysis of variance. So in two-factor ANOVA, we're going to have some factor A that has a number of levels, capital I, and then a second factor, B, which has some number of levels, which is J. So then there will be I times J different combinations. And each one of those combinations we could call a treatment. There may be multiple replicates of each individual treatment. Right, so we may run in each individual experiment, or we may have multiple observations at each individual set of conditions for factor A and factor B. And we'll call that number of replications Kij. So in today's lecture, we're going to look at a two-factor ANOVA, starting with Kij equals to 1, meaning that there's only one replicate per treatment, right, per condition. And then we'll consider what else we can do and how this might change when we look at Kij of greater than 1. Okay. So a note about this is that we may often have some factor that we think is of primary interest. This is the way our examples are going to be set up today. We have some factor that is of primary interest, but there's something else that we think we might need to account for in order to really explain what's going on. So, for example, factor A. So we might be examining the impact of different types of processing equipment on some, let's say, semiconductor process or something. But it might be that there are substantial variations from day to day, even within one particular workflow. And so, we might want to set up an analysis where we not only investigate the impact of the primary thing we're interested in, which is, maybe some piece of equipment, specific piece of equipment that we're using, but we also want to then control for or account for the impact of the day-to-day variations. And we can do this with two-factor ANOVA. So in this example, we might let factor B be different days of the week. A might be different pieces of equipment. B would be different days of the week. So we're going to start with some examples, and we'll work our way through the examples. This is another example of the type of statistical analysis that we do mostly within Python. But for example, on the exams, I'd expect you to know how to take the output from Python, just like on the previous quiz, how to take the output from Python and interpret that to answer questions about statistical significance and perform some other follow-on interpretations. So here's our first example. So we're going to say 3 types of filters are being tested for a clean room. The contamination in the room varies from day to day, right? Maybe depending on what the air quality is outside or other things going on in the building or area. So, and the filters are now going to be tested on 4 different days. And then we're going to look at the loadings on the filter after 2 hours of operation. And we need to select the most efficient filter based on a significance level of 0.05. So we have our data here, right? This is our loadings in milligram per square meter of the filter material for filter 1, filter 2, filter 3, and we've collected data on each one of these individual days. One thing to note here is, obviously we don't have to do this just with Python. So this can be done with some spreadsheet programs. So for example, we can do 1 and 2 factor ANOVA in Excel. And so one of the Excel files that was actually uploaded to Canvas in files shows you how to do this same example in Excel, should you want to look at that. But let's just summarize the expressions that we use for ANOVA and how it applies to our 2-factor ANOVA example. So in this example, we're going to say that the our treatments, right? So the primary thing we want to investigate, we'll call that A in our nomenclature from earlier. That would be the type of filters. In this case, we would say that the blocks are the days, right? So we're trying to control for the impact of day-to-day variation on the thing that we really want to measure, which is what are the different filters. Yep. Yeah, that's correct. So replications here would mean, so when we have Kij greater than 1 would mean that instead of, in this example, we said that we just had 1 measurement of each filter day combination. So that's Kij equal to 1. Kij greater than 1 would be, for example, if we had 6 measurements of filter 1 on day 1, 6 measurements of filter 2 on day, filter 1 on day 2, and so on. Yeah. Exactly. Yep. And our last example, so we'll go through 3 examples today. Our last example will be Kij greater than 1, and so we'll see that. So in our previous lecture on ANOVA, we said that the F ratio, right, or the F statistic, is given by the mean square for the treatment. And if you notice, if in the notes from that previous lecture, we just said MS of TR, because in that case, there was only 1 treatment, right? When we were doing 1-factor ANOVA. Now we have to specify what the treatment is. So we say MS of A, or the mean square of the treatment, divided by the mean square error. That determines our F statistic. So now we have 2 factors. And so now we have 2 different F ratios that we're going to be computing. And when we look at our results, our output from ANOVA, a 2-factor ANOVA, for example, in Python, we're going to have an ANOVA table. And we're going to see that we're going to have 2 different F statistics that are going to be output. So the first is mean square of A over MSE. Second is mean square of B over MSE. And this is how those relate to the sum of squares of both A and B. Again, in the same way it was defined previously when looking at ANOVA. And then if there are if there are replicates, then we're also going to have a 3rd F ratio that we can consider for interactions, and we'll look at this again in example 3. So if we had more than 1 measurement of each filter day combination, basically what this allows us to do is look to see if there's any interaction between filters and days. We'll see in an example what we mean by that later. So if Kij is equal to 1, we can't test for interactions directly. So we're not statistically justified in computing that 3rd F statistic. And so we'll just see the first 2. So in this case, we're going to have FA and FB output in our ANOVA table. So we're going to read that data into Pandas data frame. And we can see loadings and filters and days, and this is the correct format. for doing our ANOVA analysis. And we can then plot this data. And we're going to plot this data as shown below, but there's just a few things to note about the plot. So this kind of plot, so down here, we're going to plot all of this data. This is generally called an interaction plot, where we're going to be plotting our result as a function of one of the factors for the different levels of the other factor. And the way we normally choose to make this plot is we're going to try to choose, for the x-axis, we're going to try to choose something that's quantitative, just so we can really get a sense of what the trends are in these data. So in this case, we have the day is quantitative because these were taken on successive days. So the days are quantitative factor, so we're going to plot that on the x-axis. And then we're coloring these lines by the filter conditions, right? Because that's kind of a qualitative factor. I could renumber the filters and it wouldn't really affect our interpretation of these results, but I can't renumber the days if these are taken on successive days. Okay. So from this kind of plot, from this kind of interaction plot, we can get a sense of just overall, what do we expect in the data? In this case, it looks mostly like filter 2 has a little bit lower loading than filters 1 and 3. And there may be some impact of days, right, on the actual results. But now, the whole point of this two-factor ANOVA is to help us go beyond just saying this one looks like it's better, but actually make a statistically justified statement of, is it better or not, and at what level of confidence. So another thing to note about reading these plots is about interaction. So even though we wouldn't be statistically justified in making a statistical statement about how confident or not we are in there being interactions. Remember, in this case, Kij is equal to 1. We have one replicate per treatment. And so we are not going to end up with a F statistic value for the interaction term in a model describing how our result, our output varies as a function of the treatments. But nonetheless, we can see if there's some initial evidence of there being an interaction among the variables. And the way we look for that is that if these curves are all mostly parallel to one another. So for example, the curve for filter 3 roughly parallels the curve for filter 2. You see when one goes down, the other goes down. When the other goes up, the other goes up, and by roughly the same amount. So those are parallel. It doesn't look like there's any interaction between filters 1 and 3 and the day. But in the case of filter 1, it does look like there's interaction. There's at least some graphical evidence of interaction because this curve for filter 1 doesn't parallel the other ones. Okay, so when we have multiple replicates, we'll be able to test that. But here we can at least see that there's some potential interaction. So in order to do our statistical analysis, we need to define what the model is that we're going to actually use to do the analysis. And so we're going to define random variables and observed values, and we're going to be using double subscripts because in this case we have two factors, right? So we're going to have one subscript for factor A, one subscript for factor B. So we'll say that capital Xij is the random variable when factor A is at level I and factor B is at level J. Okay, so it's a random factor for a given treatment. And then lowercase xij is the observed value that we actually measured of that random variable x, capital X of ij. So that makes sense? Just nomenclature. This follows from what we've been doing since the very beginning of class, right? Remember, maybe lecture 1, lecture 2, we defined a random variable x, right, capital X, as like the whole population of all possible values of that random variable that could exist. But we don't have access to that, right? We just take a sampling of that, and we typically denote that using the lowercase, right, for an individual realization of an experiment where we're sampling the true, ideal random variable. Yes, I'm not quite sure. I'm not quite sure what you're asking me. Would you please mind clarifying? Yep. Mm-hmm. Yeah. So the question might be like, if let's say we had two categorical variables instead of one quantitative, and this were some other category, so it doesn't necessarily matter what order they're in. Can we still do the same kind of analysis or the same kind of interpretation of this plot? And the answer is yes, actually we can, because even though, okay, let's say that this is categorical. Let's replace this and just say these are random days. These are just 4 random days. Okay. So now the ordering of this doesn't really matter. It's not truly quantitative. And let's say we replace this with quantitative days over some random period of time. We can still see that we can still use this kind of a plot to say that filters 1 and 2 and filters 2 and 3 mostly have the same change as we move from this level of the categorical variable to this level of the categorical variable. And there's a different pattern that's there with filter 1. We could still make that same kind of determination. Yeah. So yes, this still works even if they're categorical. And for example, with the baseball player example. Great, good question. So, okay, so we're going to say now that our random variable xij, we're going to assume that in the case of no interactions between the two different factors, we're going to say that our random variable is equal to mu, so the mean that we get from that random variable, plus alpha I. It's like the influence of factor A on that random variable, plus beta j, the influence of our factor B on that random variable, plus some epsilon ij, which you can think of as like random noise, like random fluctuations. So this is telling me that so I have my variable xij, capital Xij. It has some big mean, right, which is kind of like the average that I would get over all possible realizations, over all the factors, all the levels, plus whatever the influence is of A, plus the influence of B, plus noise. Right, so that's our model. And our ANOVA, our two-factor ANOVA in some sense, is about trying to estimate what is that alpha I, right? What are the alpha I's and what are the beta J's? So what are the influences of A and B on my variable? And then how significant is the interaction that I've detected? Okay, so that's really what we're doing with this two-factor ANOVA. And what our conditions are that sum of all of those alpha I's should be equal to 0. The sum of all of our beta J's should be equal to 0. That's basically just saying that the overall average of all of our random variables xij's, all of our xij's is equal to mu, is equal to the overall average. okay? And so what we're looking for is the interactions that change the random variable away from that overall average, okay? And that's encapsulated in alpha I and in our alpha I's and beta J's. And then those epsilon ij's, they're assumed to be independent, normally distributed with mean 0 and common variance sigma squared. So we're assuming that there's some, so our measurements have some amount of noise that's encapsulated in that epsilon ij. And we're going to say that the mean of all of that is 0. And the variance, the variation that we get from in epsilon ij is the same regardless of what treatment exactly we're looking at. So the true grand mean average overall treatments is mu, and note this is the true grand mean, right? So it's the sort of idealized grand mean of this random variable x, assuming that we had perfect access to every possible value that it obtains. We never really have access to that, right? So we take the sample mean as an approximation of the true grand mean. So we take that x bar as our approximation of mu. We're doing the same thing here. Alpha ij is the effective factor A, and beta j is the effective factor B. So then with this setup, we can then look at what our null hypotheses are. So our null hypotheses are, so we have two of them. One is that all of the alphas are equal to 0, meaning that there is no impact of factor A on our random variable. Alternative hypothesis for A is that at least one of them is non-zero. And our second null hypothesis is that all of those factors beta are equal to 0, with the alternative that at least one of those betas is non-zero. So again, this is analogous to what we did for one factor ANOVA. Remember, in one factor ANOVA, it's like, I don't know, just crossing out that second line there. In our one factor ANOVA, the initial test that we did, right? The initial ANOVA test that we did was really just, is there any one of the conditions that is different from the rest, right? Remember in the baseball example, it was there some position grouping that has a statistically significantly better or a statistically significantly different batting average, on-base percentage rather, than any of the other player groupings. So this is exactly analogous, but now just formulated in terms of this model with alphas and betas. Okay, but it's the same idea. We're just saying our null hypothesis is that there's no effect, and our alternative is that there is some effect. Okay. So in this case, we're using Kij is equal to 1, where Kij is the number of replications. So we can now perform our analysis of the filter data and interpret the results. So in this case, we're using OLS, right? That same package, and we write our model as loading is some function of the category for filter plus our category for day. And then we're going to look to see, right? So that's stating what our model is. We're not writing in what the noise is. The noise there is implied. We're not writing in values of what the coefficients are. It's implied that those values of coefficients are what's going to be found. Yep. Yeah. So the question is, why is it a C in front? Can we change that? That I'm actually not sure of. That I'll look at and try to get an answer for you by next time. But yeah, that I'm not sure of. Yeah. That's a good question. I had the same question as I'm reading it out to you now aloud in class. Okay. But we can read this as our model is saying that the loading is a function of the filter plus the day, or the effect of the filter plus the effect of the day. And so when we generate our output, we can then see our ANOVA table. It has an extra row right over the ANOVA table that we saw with one factor ANOVA, where we now have a row for filter, a row for a day. And we can see, so now to start working our way through interpreting this, we can see that this factor A, which was filter, right, the effect of the filter, has a p-value of 0.002, or a little bit less than 0.002. So we can reject the null hypothesis at our level of 0.05, right? So that p-value is less than our stated significance. So we can reject the null hypothesis, which means that the filters, or there's evidence that at least one of the filters has a different efficiency from the rest. Again, just like in one factor ANOVA, this alone doesn't tell us which one, right? It just tells us that there's some difference. Yeah. In this case, it's really just doing it's doing the same calculation for both. The calculation that was listed above for the F statistic, where it's the sum of squared for the treatment over M to MSE. So that's really that's what we're getting here. Yeah. And if you notice here, and this also came up on the exam, this is the sum of square value. This is the degrees of freedom, right? So to get the sum of squares of the treatment, it's this over that degrees of freedom. And so from this, we can compute the F statistic, and we should, and as a check. So then our MSE is this divided by this. So, and from this, we also see our p-value for the F statistic for factor B, which is the day, also has a value of 0.0045. So it also has a value that's less than our significance. And so we would also reject the null hypothesis in this case, meaning that in this case, we'd say, practically speaking, it was important to test the filter on different days. There was a difference between the filter on different days. So it validates kind of what we saw up above here. Now note that we weren't testing for interactions between filters and days. It looks like there's evidence of interaction, but we weren't able to test because we only had one replicate. In example 3, we'll look at how we can include the possible effects of interactions. Any questions on this so far? Okay, so for example 2, this is also, again, 2-factor ANOVA with Kij equal to 1, right? So just one replicate per treatment, just a slightly different example. So in this case, we're saying that we have 4 different detergents, A, B, C, and D, being tested at gasoline additives in 3 different engines. We're calling those engines blocks. The engines in this case are our blocks. The purpose is to prevent clogging the fuel injectors. And so in this case, we measured some level of cleanness with unspecified units for each pair. Higher values is what we deserve, what we're looking for. We're looking for a higher value to indicate higher level of cleanliness. So this is our data. Again, it's in SLSX format, Excel format, and we're going to read that in. And again, we're going to start by plotting the data just as we did before. And so in this case, this is an example of, actually it gets right to our earlier question of what happens when we have 2 categorical variables, right? And in this case, the interaction plot is still of value, right? Because it still allows us to see that, these lines appear roughly parallel, although not entirely, right? So it looks like factor C, right? So whereas factor D, for detergent D, we see a decrease from engine 1 to 2. For detergent C, we actually see an increase from 1 to 2. Right? So it looks like there may be some interaction here that we could possibly hope to tease out if we had more replicates. Okay, and if we were to just swap the orders, engine 1, 2, and 3, then we should still be able to detect the same kind of pattern from this kind of interaction plot. Again, we're going to construct our ANOVA looking for detergent, the effects of detergent and engine. This is our resulting ANOVA table, where again, we're looking at our our p-values is also an example where both p-values are definitely less than a significance of 0.05. And again, we can reject the null hypothesis. So it indicates that the detergents do indeed look like they have significantly different cleaning efficiencies, or at least one detergent appears to have a different cleaning efficiency than the rest. And for factor B, we also reject the null hypothesis, implying that it was important to test the detergent in different engines, or that the different engines also had an effect on this detergent, or on the cleanliness. So in this example, we just want to compare to what happens if we were to do pairwise comparisons. And we're doing this basically to illustrate the importance of doing a two-factor ANOVA. So I'm going to scroll back up to the data, the interaction plot on the data. So let's say that we have run the same set of experiments on 3 different engines with 4 different detergents, but we didn't initially suspect that the engine was going to have some impact on our result. In that case, we might lump together all the data for D, all the data for A, all the data for B and C, and so on, and just do our ANOVA on each one of those individual detergents, again, without controlling for, or without looking at the effect of engine. So one way of looking at that is and we can go where we saw in our one-factor ANOVA, we can do all of the pairwise comparisons in a couple of different ways. We can use the Bonferroni correction, which was on the quiz. We can use Tukey method, which was, well, we'll talk about that on Wednesday. Or we can use the Tukey method, which is implemented, for example, in Python, and then look to see if there's any difference that we see between the different possible pairwise comparisons. But when we do that, and we ignore the differences, or we're maybe oblivious to the fact that there might be differences between engines, we see that we're never able to reject the null hypothesis that there's a difference between the detergents, right? So our p-values are all actually pretty large, right? And so if we were to construct the test, if we had constructed the test this way, if we ignored the possible differences between the engines, then we'd end up reaching the false conclusion that there was no difference between the effects of the different detergents. Does that make sense? Okay. So this is kind of one of the powerful aspects of this multi-factor ANOVA. Like when we have data like this, where it would be hard to reach a conclusion on the effect of these detergents just based on tests in a single engine, right? Because we might only be able to run one test of each detergent in a given engine. Or if we're talking about days, right, it might only be possible to do one test of each of our clean room filters on a specified day, right? So it would be difficult to achieve. It may sometimes be difficult to achieve a statistically significant comparison among different conditions if we only have one day or one engine to collect our data on. But there may be significant variation, not only in terms of the thing that we care about, right? So in this case, the detergent, but there also may be significant variation that's induced by some other thing, right? In this case, the engine, and our previous example was the day on which we run the test. And so what two-way ANOVA allows us to do is to separately consider the potential impact of both the thing we care about and this other thing that's also kind of along for the ride, and then detect to see if there's actually truly a difference caused by the thing that we care about, right? And that's illustrated. I mean, you can kind of guess at that here, right? If we just look at detergent D, we can see that if we were to lump all of our results together from engines 1, 2, and 3, we can see that the data for detergent D overlap pretty significantly with the data for detergents A and B. Right, so it's hard, if we were to lump all this together, it'd be hard to differentiate the effect of detergent A from B and A. Sorry, D. But again, with ANOVA, we're able to essentially control for or look at the impact of those other factors. Yeah, question.
So if we just taken presumably
Yeah, so the question is, by testing it among different, like if we had done it all in one engine, might we have been able to detect a difference? Well, it depends. If we just did one test of each detergent in one engine, then we're unlikely to have enough data to make any statistically significant conclusion. But if we had done three tests, if we were able to have done 3 tests within a single engine, then it seems likely that we would have been able to make this conclusion. But maybe a better example of that is if we go up to the clean room filter example, right? It might only be possible to do a single test of a single filter on a given day. And so what this is showing us is that if we were to run the tests of the filters, if we were to try to confine ourselves to a single day, because we know the cleanliness, the air, the level of impurities in the air varies significantly from day to day. So if we tried to confine all of our filter testing to a single day, that would mean just a single data point per filter, right? So we'd have 3 data points. We're not going to be able to reach much of a statistically significant conclusion from that, right? So practically speaking, we'd be limiting ourselves to 3 data points, right? But if we now run the experiment over multiple days, it may be the case that the variation from day to day is going to swamp out any effect of the individual filters, right? So by doing this 2-factor ANOVA, we can separately consider the variation from day to day from the variation caused by the filter, and now actually achieve some statistical significance for the thing that we care about. Does that make sense? Yeah. In the case of the engine, maybe it's only possible to do 1 per because we only have the engines available for a certain amount of time in our testing lab, or maybe something else changes in the engine after we run all of these tests or something. But yeah. Okay, so this kind of highlights the power of this multi-factor ANOVA, right? And it is often the case that we may have some other thing which affects our result. So we saw in the to come back to our hypothesis testing when we had just 2 conditions that we were looking at. We saw that when possible, we could do a pairwise comparison, which actually gets us a lot of the benefit of ANOVA. But in that case, we just need we would have a single pair, right? So we, for example, looked at air quality data from 2 different types of sensors. And we know that air quality varies substantially from day to day and from location to location. And so we put the 2 sensors in the same location, and we take measurements. We take the difference between the measurements on the same day in the same location. But now if we wanted to compare 3 different sensor types together, right? We'd want to do something like ANOVA in order to control for the day-to-day variation. Okay, so we can then, we formulated our model in terms of alphas and betas, which describe, we can think of these like the interaction coefficients. They describe the impact of factor A and factor B on our random variable X. We can actually use the results of our ANOVA analysis, right? We can interpret the results that come out of that ANOVA, come out of that Python code, to determine what those alphas and betas are, or what our best estimate of what those alphas and betas are. So in this case, the alpha estimate, in this case, alpha hat, that hat indicating, a little caret thing indicating that it's an estimate. It's this yi dot, we'll explain what that is, minus y bar dot dot, where that single bullet means that we're summing over all values of, in this case, the second variable. So in this case, we're summing over all values of j. So it's the average for each condition I summed over all values of j, minus the overall average in this case. So summed over the average of y summed over all ij. And similarly, we can estimate beta hat, or we can estimate our individual betas as the average for an individual level of B, right, J, over all levels of I, minus the overall average over all possible values of I and J. So we can estimate this using code from our results by looking at the overall mean, right? So we have our overall mean. We can look at the averages over each one of those individual values, which are given which would give us the result of these individual y bars that we would like. So in this case, we're grouping by detergent. We're taking the mean group by detergent and the mean group by engine. And then we can then find, once we have the mean group by detergent, or the mean group by engine, the mean group by factor A, the mean group by factor B, we can then find the overall averages of each one of those. So the mean cleanness for detergent A, the mean cleanness, for example, for engine 1. And from that, we can find our effects, our alpha i's and our beta j's using the formulas that are given above. In this case, we see that we end up with an estimate of that of the alpha parameters for each one of our detergents, A, B, C, and D, showing that our estimate of detergent C, for example, is the largest here. And we're saying that our estimate is that detergent C has the biggest impact on our cleanliness, or the biggest positive impact on our cleanness factor, whereas detergent D, our estimate is that detergent D has the worst impact on our cleanness factor. And if we go back up to the data, we can see that this is in line with what we would expect, where C looks like it has the best overall result. Again, higher is better, and D looks like it has the worst overall result, right? But now we've actually been able to put numbers onto that and see, how much better is potentially C than D. And we can do the same thing so here we're just formatting that result. And we can do the same thing for engines as well. It looks like, and this would tell us that engine 3 overall has the strongest results, or has the cleanest results. Again, agrees with our interaction plot above. Yep. So is the alpha I dot beta I dot only for replication equal to 1? So I do not believe so. I believe that applies if we have Kij greater than 1. Let me double check that as well, but I believe that applies for Kij greater than 1 as well. All right, I have 2 things to follow up on. One is the C in our syntax, and the second is is whether or not those apply for Kij greater than 1. Okay. I'm gonna have to write those down at the end of the lecture. So, all right, so let's look at our third example, which is for Kij greater than 1. So now we're going to also include interactions between elements, and we'll be able to obtain a valid statistical test for possible interactions between elements. So go beyond just saying graphically, it looks like there may be some interaction. So in this case, we're going to look at 3 different varieties of tomato and 4 different potential planting densities. that are being tested for planting. And what we want to see is we're looking at the overall yield that we get by planting in 3 different plots per pair of tomato variety and planting density. So the data is summarized below in this table, and we'll scroll down, look at the rest of the table. But the question is, what are we going to recommend to the tomato farmers? In this case, note we're using a significance level that's a little bit more stringent of 0.01 instead of our 0.05, which is sometimes customary. Yeah, so we want to know what should we recommend, right? This is our data. What do we recommend? So, and again, this is done in Excel. It can be done in Excel as well, and I provided an example file for that. So our data is read in again into a pandas data frame, and we're going to start as we have previously with an interaction plot. So in this case, it's the average yield. So we're looking at the average for the replicates is what's plotted here as a function of density, right? So we had that quantitative variable, so we're going to put the density on the x-axis, and then our qualitative or categorical variable was the strain, and so we're looking at this here. So from this, we can already see that it looks like, right, that variety P is better than the other varieties, right? Remember, we're only plotting the average. We're not plotting actually all the individual points, so it remains to be seen if it is statistically significant relative to the variation that we see within the data. Yeah. Yeah. So when we do this interaction plot, it does automatically give us the average for each condition. That's correct. Yeah. Okay, so it looks like that. And when we're thinking about the interaction, right? Remember what we would see, our evidence of interaction would be if these lines are mostly parallel to one another, and that would indicate that there's no interaction. But if there's some deviation from that, then that would indicate that there is interaction. And here it's a little bit uncertain, I'd say, just from the plot alone, whether or not there is an interaction among the variables. It certainly looks like, right, for this variety H, it doesn't go exactly parallel to what we see for variety IFE, for variety I, but we'll see if it's significant or not relative to the variation between the samples. So now our formula for OLS includes the impact of variety, the impact of density, as well as the impact of both variety and density, and this is that interaction term, right? So that we're actually including that interaction term explicitly within our model. And so then we're going to end up with, remember up above, we defined the F statistics for our different variables, for the impact of our different factors, rather. And we defined an F statistic for the interaction. We said we're only going to be able to use that when Kij is greater than 1. So in this case, when we define our model for OLS, including this interaction term, we're going to get that third F statistic, and we're going to be able to look at the effective interactions. And so when we run our ANOVA, this is what we get. We're now, again, we only had 2 factors, variety and density. We have 3 rows here, or 4 rows here, but we have an extra row here from what we had previously, and this describes the interaction, right? Where this is our F statistic for the interaction, and this is our p-value for the impact of that interaction. So again, we can see that it does look like there is an impact of variety and density, because the p-values are definitely lower than our significance thresholds, in this case of 0.01, right? So it does look like there's an impact. But in this case, we would reject the null hypotheses for both of those cases, right? For there being no impact of variety or density. But at our specified level of significance of 0.01, we cannot reject the null hypothesis that there's no effective interaction. So that effective interaction, although it looks like there's some small effect at the level of, at a p-value of 0.01, at the significance level of 0.01, there's not enough evidence in this data set to conclude that there isn't an interaction among those variables. Um, so we conclude that different varieties affect yield, and that yield also depends on plant density, right? So both of these things play a role in what our overall yield is. So from this, right, it does look like this P variety does better than the others. It also suggests that there's an optimum density, right? It looks like there's some kind of an optimum density somewhere around 30,000, whatever units that is, right? So that'd be the recommendation to the farmers. Okay, and then one possible interpretation is given here as well, that it suggests that more seed is advantageous until crowding starts to limit yield. So at some point you get to a too high of a density and you start having reduced yield overall from your crops. But this is now two-factor ANOVA for Kij greater than 1, where we're also able to look at interactions. Any questions on this? Yeah. Great question. So the question is, so at the beginning we said it was measured over different plots. Could we extrapolate from two-factor ANOVA to three-factor ANOVA? And yes, and that's what we'll do on Wednesday. So on Wednesday, we will look at P-factor ANOVA, where we can extrapolate to more than, to many more factors. Any other questions? All right, then thank you all, and I will see you on Wednesday.